Still there and still okay.
Still here and still okay.
All right, great. Thank you. Okay, ladies and gentlemen, thanks for joining us today. This is Bob Weber at Kansas State. I'll be hosting today on behalf of Dr. Dare Bullock and Dr. Matt Spangler, my colleagues at University of Kentucky and University of Nebraska, respectively. And we're in the 2017 installment of the National Beef Cattle Evaluation Consortium's Brown Bagger series. So this is our first session, and first off, appreciate everybody's patience and persistence in our registration process this year. We've shifted platforms here at K-State and moved to Zoom, which I'm pretty confident is going to work really well. Just had some kinks to work out in our registration process, and appreciate everybody's patience getting through that. Today's session is October 4th under the overall program title of National Cattle Evaluation, Charting a Course for Continued Genetic Improvement. And as Matt and Dare and I worked to put the agenda together, we thought maybe right up front is a little bit of discussion and education regarding the new single-step processes being implemented around the industry. And as educators and technical folks in the audience, I'm sure you'll appreciate both the monumental amount of work that's gone on into developing and deploying this new technology, but also we'll be charged with providing a lot of education and outreach activities related to Singlestep. And so we thought it'd be really helpful to have two of the principal scientists involved in that process present to us today. And so our first session here is titled Latest Advancements in National Genetic Evaluations, Conversion to Single-Step. And we'll have presentations by Dr. Stephen Miller. He's Director of Genetic Research at Angus Genetics Incorporated, and also Dr. Bruce Golden, the principal scientist, one of the principal scientists there at Theta Solutions, and he's got a couple of well-known partners who I'm sure he'll reference and introduce in his discussion. And Bruce will be talking about deployment of Bolt at both American Hereford Association and IGS. So with that, we'll start through a few slides here. First off, just for reference, our recordings of these presentations, when we get them processed, will be posted up under the For Professionals tab on the NBCEC website. And you'll be able to go back and listen to these presentations in their entirety for future reference, or point other folks to these recordings. Again, I'm Bob Weber, one of the partners in bringing the webinar to you today, and I'm a faculty member here at K-State. So again, our two speakers, Dr. Stephen Miller and Bruce Golden. We'll start our discussion today with Dr. Miller. His title that he sent is After 7-7, Genomic Implementation at AGI. So as many of you know, in July on the 7th, they switched over from the previous NCE methods of weekly evaluations to a new single-step procedure. And Dr. Miller's been an instrumental figure at the animal breeding community for a long time. A recent add to the staff there at AGI, where he serves as Director of Genetic Research, based in St. Joe, and he leads the organization's research and development efforts and furthers the innovative evaluation methods for the association's weekly national cattle evaluation for both Angus and other AGI clients. Steve's originally from a beef cattle farm in Canada, and obtained his doctorate in 1996 and bachelor's degree in 1992 from the University of Guelph in Ontario, Canada. While Steve was completing his PhD, he was a visiting scientist at Animal Genetics and Breeding Unit in Australia, specializing in beef cattle. And most recently, Dr. Miller was a principal scientist with the Animal Genomics team at Ag Research Limited in New Zealand. His previous role was a director of the Center for Genetic Improvement of Livestock at the University of Guelph, and that's actually where I first met Dr. Miller at a Kennedy Colloquium there in Guelph, and worked on industry adoption at the University of Alberta's Livestock Gen Tech Center. Dr. Miller was on faculty at Guelph for 14 years, where he led a research program in the genetic improvement of beef and dairy cattle, sheep and turkeys as well, and with a special emphasis on improvement of efficiency and meat quality traits with an industry application emphasis. So one of the things I've always appreciated about Dr. Miller is he's a great theoretical scientist, but really focused on application and deployment of technology in the beef genetics sector particularly. And so we appreciate that very much about you, Steve. Over the course of his career, Dr. Miller's had nearly 20 years experience in beef cattle selection, genomics, and technology. So with that, Steve, if you'll, I'll unshare here, and if you'll pick it up, the floor is yours, and we look forward to your comments.
Thanks, Bob, for that introduction. I just checked that everyone can see those slides okay.
They look good.
Okay. So it's been a year. I've started here at AGI, and it's in September of 2016, and one of my first jobs was to present on the brown bagger about this time last year. And we talked about Singlestep and the fact that we had it running side by side with our current methods. And at that time, we didn't realize exactly when we were going to implement it. We still had some questions that I'll go over today. But as you've mentioned, Bob, on what we call 7/7 or July 7th was a big day for Angus breeders, because that was the day we finally released the new evaluations. And what I'd like to focus on today is not kind of rehashing a lot of what we have presented. We have on Angus, if people go to Angus.org, there's some pre-recorded webinars and things that we've done about more detail of the results from Singlestep on July 7th. What I'd like to focus on today is kind of the questions that have come up from breeders, and the ones that we have to answer, and how we're going about answering them. And it's been an education in itself, I guess, as you try and explain differences to breeders, and it's actually highlighted something, and that is Mendelian sampling variation as kind of the root of differences that we see in animals and their EPDs, and just explaining that process. So I'll zoom in on that today. So when we made our presentation last year about this time, we realized we had new results from Singlestep, and we had the results that breeders were getting every week, and they were different. And at that time, we're trying to figure out, well, they're different, but are they better? And between September last year and July, we did some research to verify that they were better, to give us confidence to turn them over to breeders here on the 7th of July. And so I used and then of course breeders say, well, you've given me something that's different, and you've re-ranked my animals, which is obviously disruptive for them. And the point it we're trying to make is, well, we couldn't give you something better that wasn't different. And so that was something that the industry, July 7th created a lot of interest in the industry. Obviously, animals re-ranked, especially younger animals, and this is just one of the articles that came out about it at the time, in terms of being a game changer. And if you can read one of the sentence here at the end, as a result, seed stock and commercial producers have some readjusting to do, as some bulls won and some lost. And that is and that's part of what I'll answer today, is kind of answering the question, why did this animal change, and why are they different? So we talk about Singlestep a lot, and that's obviously a big change that happened on the 7th of July. But it's important to point out some other big changes that all happened for us anyways at the same time. And the one is we improved the model quite a bit for carcass traits, and that created some big difference for traits like carcass weight. The new Singlestep evaluation brings in all the new data and all the new genotypes, so it's right up to date in terms of what's available, and which includes a lot of additional genotypes for Angus. As well, we also updated all the heritability and genetic correlations, so like our genetic, what we call our genetic parameters, as well as updating, which we do annually anyways, the economic values that go into the indexes. So July 7th really was a big day because it incorporated basically all these changes at once. I want to point out the team behind this. You know, I'm there, but you know, I've been here for a year, and essentially Singlestep was already running when I showed up, and I joke sometimes that, you know, I showed up in time to catch the baby, but a lot of things had already been in place before I got here. My colleagues Dan and Kelly do a lot of the work in terms of communication and interacting and answering questions for members, which is greatly appreciated. Li-Shen Wang did a lot of the work in terms of estimating parameters and model development. And our bottom row here, led by Luann Adams, is a great team of programmers and database people that actually run these programs every week. I just checked last week, for example, the growth run includes 15,000 new animals with about 2,500 new genotypes, and that's happening every week. And every week that data is coming in and new evaluations are going out. And so on top of that day job, we were dumping on them, here's new models to try, and running all these things in parallel and checking and double checking. So very appreciative of the team that puts this together. That's the team at AGI. The software that we run is developed at the University of Georgia, and Daniela Lorenko has been our main contact person and a great support, as well as the whole team in terms of answering questions about the software, making changes so we can implement it. I want to point out, I'm just getting some feedback there now. Yeah, I just want to point out, with our implementation of Singlestep and Georgia software, we're basically running GBLOP, and we're not running a weighted SNP model. The scientists at Georgia, Daniela Lorenko and others, have been investigating that. You know, what would be the advantage of a weighted model? And it appears with our large database of a lot of animals genotyped and the polygenic nature of the traits that we're dealing with at the moment, that there's not a big improvement in accuracy for us to move to a weighted model. But it is something that is available with the software and something we'll continue to evaluate. Just an idea of, you know, where's our data set up to at the moment, and part of this, you know, implementing Singlestep is just the size of the data set. And we're up here with close to 9 million animals in the growth run. There's 22 million animals in our pedigree file. And when I started at Angus here just a year ago, we talked about the number of genotypes, and that number started with a 2. It was 200 and something thousand. And today that number starts with a 3, and it won't be long if we continue to put in genotypes at over 2,000 a week. You know, 10 weeks from now, we'll probably be starting with a 4. So the data set in terms of number of genotyped animals is growing very rapidly. So as we were evaluating Singlestep and determining when we're going to switch and how to switch, one of the things we were looking at was our genetic trends. And what we find with Singlestep is if we run Singlestep, or we run a model that doesn't include genomics at all, which we call our kind of classic model, that the trends are almost identical. And this is what we'd expect. What we found with our previous approach, our multi-step approach, is that we had trends that could deviate quite a bit. Marbling was one of those, where our trend for marbling was higher with our two-step approach or multi-step approach than what we have with Singlestep. You know, the fact that we've got trends with Singlestep, very similar to classic, is actually an indication of the fact that Singlestep is not overinflating predictions like the previous approach was. And I'm hitting the highlights of some of these things. Again, the webinar that's available on the web has more details about the different traits and the different trends that we realized. But the one thing that Singlestep allowed us to do is it was a much simpler model. Our previous approach, we had to fit correlations with all of these genomic predictions with the different traits, which increased the complexity of the model. With Singlestep, because the model's simpler, we don't have to fit all those extra traits. We can add some traits to our model and still deliver a weekly evaluation. And so our carcass model, what we added was we added weaning weight and fat to our carcass model. And with weaning weight, as well as scan weight or yearling weight, we can account for pre-selection. You know, the average animal that goes on to get scanned is not, likely doesn't have an average weaning weight. And we can account for that pre-selection bias that was creeping into our previous model. And we can also account for fat depth and fatness in those animals, which is an indicator of maturity. And basically by including those traits, we're actually doing a better job or more accurate job of evaluating carcass weight now than we were previously. This is what our carcass weight EPD trend looks like now compared to previously. Previously, it was basically maybe overestimated our trend due to two-step, but it was underestimated because we weren't accounting for pre-selection bias. Now with Singlestep accounting for pre-selection, we basically have a trend in carcass weight EPD that's very similar to what we were showing before. One of the things we did not have in hand when we presented at this time last year, when we were trying to determine was Singlestep actually an improvement, was some important validation work. And part of that was validation work with the Mean Animal Research Center, where we took our Singlestep EPDs as well as our previous EPDs and compared them. How do they correlate with EPDs that would be generated from the USDA MARC data? So we did this in collaboration with Dr. Larry Keane. And it's important to realize that the USDA MARC data, although they have data from 196 different Angus sires, that data is not in our database. So it provides an independent validation. And what we see here on the right-hand side, you see Singlestep and you see here multi-step. And basically the Singlestep EPDs are more correlated with what happens in that independent population at the USDA than what we were doing. And with some important traits to point out, traits like fat here, marbling, some significant improvements, ribeye area as well. You know, these carcass traits where we've improved the carcass model have actually increased in accuracy over what we were presenting. So that's the carcass traits, and that was, I think, a really important validation and a bit of a turning point for us to get those results. And we're thankful to Larry Keane and the USDA for doing that. But we did some work with our own data as well, where we did what we call a forward validation. You know, we cut the data off back in 2015 at the time of our previous multi-step calibration. And we said we've had a number of animals come in with phenotypes since then for birth weight, weaning weight, yearling weight. How do the predictions that we generate with multi-step and the predictions we generate with single-step, you know, how do they predict future performance? And what we find is that in all cases, our single-step predictions are more accurate than the multi-step predictions for birth, for weaning, and for yearling gain. So again, our own data at Angus was saying what we're producing in terms of an EPD from Singlestep is better, as well as USDA for our carcass traits was better. So that's kind of a highlight or a high-level overview of kind of what went into July 7th. And since then, breeders have been presented with a new set of EPDs. And so what I'd like to talk about now is, you know, what causes the phone to ring here at Angus. And these two things capture a lot of the calls that come in. And the one is, you know, how can we have two flush mates that are this different on EPDs? And also, why do we have genomic scores that don't match perfectly to our EPDs? And I'll dive into each of these. In the previous system with multi-step, you know, we had molecular breeding values on animals based just on genomics, and they went into that model as a correlated trait. And all of those molecular breeding values were basically considered to have the same accuracy. And I call the multi-step is kind of a one-size-fits-all approach. You know, you get a genotype, you score it based on that equation, and that score goes into the model, and all scores are kind of considered equal in terms of their value or their accuracy. Where single step is different. We could have two animals with obviously different genotypes, but how those animals are actually tied back to data makes some genotypes more accurate, or the genomic values on those animals more accurate than others. And single step actually accounts for that. And so this kind of one-size-fits-all approach doesn't apply anymore, and we have a more kind of eloquent, a more accurate weighting of the different genomic information that goes into those EPDs. The other part of the question is, you know, why do we see full SIBs? How can full SIBs be so different? You're predicting very different EPDs on two animals, and they've got the same parents. Well, this range in full SIBs has been known for a very long time. And the picture of the gentleman here, it's not David Letterman. Picture's a little bit older than that, but Gregor Mendel is kind of famous. I think anyone who's taken a course in genetics has probably been taught about Mendel and his selection or his work with peas and tracking the traits in peas, where he basically showed we get this assortment that's happening. And in animal breeding, we talk about Mendelian sampling. And so I'd like to dive into Mendelian sampling, because if we find ourselves talking to breeders again and again about Mendelian sampling, and in some cases, you know, it's something that they really haven't considered having an impact as much as it has before. The pedigree and how that's actually incorporated into the model is really what single step's doing. Single step is instead of fitting a pedigree based just on who your mom and who your dad was, with basic rules about how you might inherit your DNA, single step is actually building a pedigree now that's based on genomic information. So based on parents, we'd expect a progeny here, X, to get half its genetics from its sire, and then that sire got half from each of its parents. So on average, we'd expect that calf X here is going to get half from its sire and a quarter from each of these grandparents. With genomics, we can actually track the inheritance of the DNA segments from each of these grandparents to the offspring, and we find that sometimes we might get a quarter from each of these grandparents, but there can be variation amongst that, and that's the essence of this genomic relationship matrix. So trying to illustrate this now to breeders, or get them to realize, where does this variation come from? And that is, we have here I have my sire, and I've got 2 chromosomes, and obviously there's kind of 29 pairs of chromosomes that we track in cattle in terms of making a genomic prediction at the moment. And so let's say this is 1 pair of chromosomes for chromosome 1. So this sire inherited 1 chromosome strand from its dam, and that came in the egg, and it inherited another chromosome strand for chromosome 1 from the sire that came in that semen, and we call these 2 gametes came together to form this animal, which is diploid, or it has both copies of all the genes, one from its dam and one from its sire. Now this sire obviously has to create a sperm cell that's going to go on and generate our progeny. So when he generates that, and he has to pass on basically 1 strand of chromosome 1, not a pair, but just 1. Is he going to pass on the blue strand that he inherited from his sire, or is he going to pass on the pink strand that he inherited from its dam? And the reality is he actually passes on a mixture of the 2. You know, just to kind of show it here schematically, you know, we get this sampling of the chromosome. So in this case, let's say it's half and half. Just for illustration purposes, we generate a calf now that the sire passed on 1 strand from chromosome 1, half that came from his dam and half from his sire, which makes this calf a quarter related to each of the grandparents. And the other chromosome here is what came in the egg to generate that calf. And we'll just put it there to illustrate it, but we're not going to talk too much about that. But that fits our pedigree relationships, but in reality, chromosomes don't break in the middle like that every time. We get variation amongst that. So let's say the chromosome didn't break in the middle and it broke as such. Now we're going to generate a calf that actually did inherit 25% of its genome from that sire. It inherited less than that and inherited more from this dam. So now instead of being 25-25, it's more like 1/8 related to the sire and 3/8 related to the dam. Or we can get a double break. And here we got a calf now. May have also inherited half its genetics from both, but it's different genetics because it's got different end of the chromosome compared to this animal. And the reason we can track this with our genomics is we have this high density genotype information where we have SNP markers that are spread throughout the genome. So we've got SNP markers all through this end of the chromosome, all through here and all through here. And the algorithms are actually tracking that inheritance. And that's why we can build a very accurate pedigree relationship matrix with the genomic information as opposed to what we can do with pedigree. And that's why the genomics is picking up variation, this calf being more related to the dam than this calf, and our pedigree just can't do that. So genomics or Singlestep is picking up that variation. It's expressing it as differences in EPDs in individual animals. And breeders are asking, well, is this variation, is there a mistake, or is this actually real? Does the variation actually match what we might expect in theory? And the answer is it does, and I'll show you that. But just work through now the variation that we see in animals. This is our phenotypic variation for birth weight. The mean is 78. We have some variation around that. Part of that, just under half of that variation is genetics. And that genetic variation gives us variation in EPDs. The variation in EPDs is actually can be split into 4 components. How much variation was in the sires and dams, and finally, how much variation comes from this Mendelian sampling. And what we see is half of the variation is actually due to Mendelian sampling. It's actually due to the combination of the chromosomes. So we can have, and this is an example with 646 ET calves from commercial receps for birth weight EPD. And these, I've centered them all on 2 pounds. So I've made the parents average 2 pounds, which was the average of the parents anyways. But what we see is, and this is EPDs that have gone out the door. These are EPDs that breeders have seen since the 7th of July. The equivalent of mating 2 parents with a +2 birth weight EPD, but some of these calves are getting birth weight EPDs of over 5. And breeders are saying, is this actually possible? You're telling me I've mated a sire and dam with a +2 birth weight EPD, and you've given me a birth weight EPD on the calf of +5. Is this actually possible? And checking with Mendel and quantitative genetic theory, the answer is yes. That is actually, it is actually possible. So to check this, I did some simulation looking at the population parameters that we have in Angus for genetic variants, and simulating 1,000 progeny from mating a +2 dam to a +2 sire, we actually get a bigger range even than what we've put out the door in terms of EPDs. And this is because this is actually a range in theoretical or true EPDs. And since our EPDs that go out the door don't all have 0.99 accuracy, we don't predict as much range. So in theory, we could actually have animals with EPDs. And as our genomic predictions get more accurate, we'll predict more range. So we can actually start to predict more range, even animals above 0.5. So that variation is, it's a lot, and but it is real, and it is what we expect. And it's kind of been a continuous communication effort. And I think for the educators and extension people on the line, anything that we can do or you could do to help better get this message out about what Mendelian sampling is and why we see this variation. And it's actually it's actually to be kind of, I guess, embraced or harnessed by the breeders, because that's the power of selection, actually identifying, here we got 10 flush mates, this allows you to actually pick the best ones. The next thing I'd like to talk about is what we see. Again, these kind of one-size-fits-all genomic scores that we calculate aren't perfectly correlated anymore with how genomics is influencing single step. And I have an example here, SIB-A and SIB-B. This is a real example. I've taken the names off. But here we got a SIB-B here. He's got a plus 2.5 birth weight EPD versus a 1.6, although he has a better genomic score. How could that be? And so we actually looked through the pedigree on these two animals to see, well, is it actually more related to some of those ancestors with higher birth weight EPDs? And so this is just the top side of his pedigree, I guess we'd say. This is his sire and the top side of his pedigree. And we've looked through here for we've looked through the entire pedigree, or the 7 generations anyways, for any genotyped ancestors. And then we looked, how is that animal genomically related to these ancestors? I'll just use one here for an example. Sherbrooke-Shoshone. How much DNA from Sherbrooke-Shoshone would we expect?
Hello, Steve. We lost your share. If you're still.
Yeah, I don't know why the it just came up my.
Right. Everybody, stand by. We'll.
Where did I lose you?
You were just starting to talk about the expectation of the genomic content of the calf relative to Sherbrooke-Shoshone.
Gotcha.
Which I was at the edge of my seat.
Can you see me now? Or am I not sharing?
Yeah.
It just, all of a sudden it just popped up and said, PowerPoint's restarting. And I said, oh, that's great.
Super. Okay. Okay. We're in, I can see your edit mode. And hey, somebody else has a big pile of document recovery. Awesome.
How's that?
Perfect. Okay.
Okay.
Thank you, Steve.
So just in theory, as we work through Sherbrooke-Shoshone down to this progeny, again, passes half on to his progeny, half, a quarter here to AA Nutrand, half of that, et cetera, down the pedigree. We'd expect 1/64 of Sherbrooke-Shoshone to show up in this calf. But when we actually track the genomics, what do we see? So I did this for all the kind of ancestors in the 7-generation pedigree that are genotyped, and you see them listed here, and a lot of, for those involved in Angus over time, a lot of well-known characters, I guess you'd say. And you see here, some of these animals show up multiple times. Here's Power Play is actually in that 7-generation pedigree 5 different times for this animal. Precision 1680 3 times, et cetera. What I did was I said, well, what would be the expected relationship from our animal and that ancestor? But what's the difference in the relationship we actually see between the full SIBs? And what we see here is that one full SIB is actually 0.02 more related to Gridmaker than the other. This is actually a 48% increase in relationship. This Rito bull here, for example, we've got 200% more of that animal than we'd expect in one of those full SIBs. And I sum them up, and some go up and some go down, but on average, when I look at, I've got them ranked here based on birth weight EPD, and when I look at that, the calf with the bigger birth weight EPD is actually more related, on average, 15% more related to these high birth weight ancestors. When I look at the other side of the birth weight table, these animals, the ancestors that were low birth weight, he's less related. So it was a nice example where here are 2 full SIBs. They've got different birth weight EPDs. Why do you think this animal is 2.5 versus 1.8? Why do you think it has a bigger birth weight EPD? Well, when you look at the ancestors in its pedigree, it's basically inherited on average, more DNA than the other one from the high birth weight bulls and less from the low birth weight bulls. And that is essentially what's driving that EPD in that calf. So just as in summary of the changes, we see a narrower range for some traits like heifer pregnancy, for example, but greater range for others. Traits like growth, for example, where our genetic trend has gone up slightly. The change has been pretty minimal for proven animals. Again, once an animal's got lots of progeny, genomics does not rock them very much. But these young animals, their EPDs are influenced a lot more by genomics, and so they've changed considerably more. And that's where most of our questions have come in on, as well as just this variation among full sibs. Again, breeders calling in, you know, is this actually possible? I think they're just seeing more range than what they're used to. As the genomic predictions become more accurate, we'll see more range predicted in those full sibs. But the one thing that we have appreciated since kicking off here in July is just the fact that the EPDs that go out every week are using all the information that's come in. And again, you know, just in the past week, 2,500 new genotypes, you know, all that information is in those EPDs, so they're most as accurate as possible every week. And I'll end there.
Great, thank you, Steve. That was excellent and really interesting, and I like the connection now back to the Mendelian sampling. That was well laid out, and I think provides a lot of clarity for participants to sort of understand how we adjust those grandparent relationships effectively through the genomics. That's really good. So yeah, if you'll unshare, Bruce has already got his up and running here. That's fantastic. Bruce, let me look here and see if we've got audio from you. Bruce, can you hear me?
Bruce, you'll need to unmute your mic.
Bruce, I think I undid it for you.
Oh, I just got it.
Okay, there it goes. Cool.
Restart here. Can you see it?
Yeah, now we're up in slideshow mode. So
super
excellent. Great. Well, our next speaker is Dr. Bruce Golden. Bruce is one of the principals at Theta Solution, and his partners there are D.J. Garrick and D.P. Garrick. And Bruce is going to tell us about their experience and some of the features and methods used in the American Hereford and IGS evaluations that are moving to a single step process using the Bolt software developed at Theta Solutions. As a bit of introduction, Bruce was Chief Executive Officer of a biomedical instrument technology company that he founded after a nearly 20-year career at Colorado State University, where he was a full professor in animal breeding and genetics. That's where I got to know Bruce. I was an undergraduate when he was on faculty there, and took a couple of courses from Bruce and TA'd a class when I was in grad school. Dr. Golden's also been on faculty in the department head at Cal Poly San Luis Obispo, where he innovated novel graduate degree programs and raised substantial funds through both research and advancement. Dr. Golden's research and service to industry has resulted in numerous awards and publications, including a series of patents related to animal identification and diagnostic instruments. So really an innovator as well as an outstanding animal breeder. While Bruce was at Colorado State, he was the founder of the Center for Genetic Evaluation of Livestock, or CGEL is what we used to call it. They were a provider of genetic evaluations for a number of breed associations, and breeding companies around the globe. He has extensive international experience in livestock production, including working in China, Brazil, Venezuela, New Zealand, the UK, Canada, and Australia. Dr. Golden attended Washington State University in Pullman, where he received both his Bachelor's of Science and Master's degree in Animal Science. And he received his doctorate in animal breeding and genetics from Colorado State University in Fort Collins. As a founder, Bruce serves in dual roles as both the Chief Executive Officer and President of the Board for their new company, Theta Solutions, LLC. So with that, Bruce, we're pleased you've joined us today, and look forward to your comments here regarding the AHA and IGS evaluations.
Thanks for that, Bob. And thanks for inviting me to be part of this excellent program. I've always enjoyed these brown baggers, and good to see you're keeping it up. So as Bob mentioned, I'd like to talk about a couple of projects that we're working on right now. Our company, Theta Solutions, is engaged by a number of clients from around the world. Two of the clients include the American Hereford Association, and that's actually in collaboration with ABRI in Australia, who provides to the American Hereford Association their data management services and has provided in the past their genetic prediction services. They're migrating to the Bolt system with an anticipated release, a targeted release right now of sometime in November. So we're very close. The software's all in place and been validated. We've automated the turnkey on the software and also on the genomic pipeline, which we also supply that service to this evaluation. So the data come in weekly to a compute engine. The engine then picks up the data, goes out and grabs the most recent genomic information, processes it, prepares it for the analysis, puts it back on the analysis machine, and then on an automated process, a daemon starts the analysis, and within 24 hours, results are available. So it's ready to go, except for a couple of final pieces on the back end and a little bit on the front end through ABRI, and we anticipate that being completed for testing within the week, really, at least by next week. So it's very, very close to running. One that has been a little more difficult to get out the door is a much larger analysis, the International Genetic Solutions Analysis. It is very large. It's about 17 million animals before pruning on it. About 350,000 new animals come in each year. And right now there's about 85,000 genotypes, and that grows very rapidly at every poll every week also right now. There are 13 partner breed organizations in this evaluation, and so that's, you know, a lot of organizations to coordinate and manage. That's done through the Simmental IGS partnership, getting the automated data extracts and then merging those things has been done by Steve McGuire with Simmental. He's done an excellent job, but it's taken a long time and a lot of effort to get those things to where they stitch together evenly and reliably at each data poll. We have prototype EPDs for over half the traits completed now and are out in review among the partners, and as you can imagine, that quite a few questions get generated as they start looking at these things. A lot of it along the lines of what Dr. Miller described. It we're going through the same kinds of processes, but what we've chosen to do is we have kind of a hierarchical level. So in the Hereford evaluation, we have worked with the Hereford Association, the American Hereford Association, to form what's called a smell committee, where it's a group of about half a dozen real good performance-minded breeders who work well together and work well with the organization, get the first crack at the EPDs to look at them. They ask excellent questions. They really, they'll see something that doesn't feel right to them, that doesn't smell right to them, and they send us back and we dig through it and ensure that we have explanations for it. Along in that process has been a real great learning experience. They've taught us a lot about how to talk to the breeders about the changes that the breeders are going to see. And how to communicate them, and getting their buy-in and their ownership really is, we feel, essential to getting the larger membership's buy-in and ownership of the change in results. We're going through a similar process with Simmental Association, but as you can imagine, it's a little more hierarchical. It starts first at the Simmental, where they have a smell committee. There's also a committee of geneticists that are reviewing results, and not until those two committees are satisfied do the prototype EPDs go out then to each of the breed associations, and we're encouraging each of the remaining dozen breed associations to also go through the same kind of process. And so we're making ourselves highly available to those organizations to help them work through the changes that they're seeing. Because as Steve said, they are going to see changes, and the changes will have explanations. And we just have to work through a process of how to communicate what those explanations are to each of these 13 breed associations. The models that we've implemented are follow generally along the lines of the single-step super hybrid model described in Fernando et al. In that paper, there's two models described, two marker effects models. They're really equivalent models. They're just reformulations of the same thing so that things predict slightly differently. And which one you choose really depends upon what the proportion of genotyped animals to non-genotyped animals there are in the analysis. So we're using the one that in the paper, I think it's called the hybrid model, but in our lay discussions and all our other work, we call it the super hybrid model. It fits genomic effects, so we actually get predictions of the genomic values out of the model itself without any solving indirectly for them. Fits extra polygenic effects, which are not described in Fernando at all. We haven't published that paper yet, but there is extra polygenic effects in the model, so genetic effects, additive genetic effects not described by the markers. It uses markers that are selected by a Bayes-C pi variable selection method, and that's what Steve referred to. It's analogous to a weighted marker model, and I'll talk a little bit more about that in a couple of slides coming up here and why we like that method. The IGS models also include a couple of features that we think are novel in these genomic single-step methods. One of them is including external EPDs. We've worked out a method that is based on the original method that Zwing and Quas worked up for including external EPDs, but there were limitations on that method, and we worked through the algebra to figure out ways that we can include much more external EPD information than was allowed or available in the past. So we include external EPDs from other sources in that analysis. And we have additive genetic groups in that model for breed by year also. So there's a lot of moving parts in this model. AHA, the significant features are there's also additive genetic groups for origin by year. And so sort of a theme that happens then as you do this, if you're going to make changes over to a single step analysis, you might as well look at other things that you can do to improve the quality of the analyses. And one of the things that we did in the Herefords was they began their whole herd TPR program, their total performance recording program, in 2001. So 16 years ago. And we said, what if we just use data only from the TPR program forward, from that date forward? Because we know that there's recording bias in older data and potentially substantial recording bias. And we looked at it, and sure enough, there really was substantial recording bias in the whole herd TPR data, the non-whole herd TPR data prior to the implementation of that program. And so we ran the analyses in all kinds of ways, doing different date cutoffs. And we determined that if you look at the animals who were under selection, so let's say that's arbitrarily any animal born, let's say in the last few years, let's say 3 years, and the parents of those animals, well, those are really the animals who are active selection candidates. What happens to their EPDs if you restrict the data to whole herd TPR forward? And what we determined was the EPDs have a very high correlation. We're at 0.98 to 0.99 if you use all the data for those animals. So we looked at that and we said, well, pretty minimal impact on cutting the data out prior to the implementation of whole herd reporting on the most recent animals. Obviously, older animals are more substantially impacted, especially older sires whose majority of data came from before whole herd reporting. But if they really aren't involved in selection in current generations, then really, it's not, the loss in accuracy is more than made up for by the reduction in reporting bias we felt. And so Hereford has made the decision after a great deal of discussion internally that it's a good thing that they will only use data from whole herd reporting forward, implementation of whole herd reporting forward. And I really think that was a real progressive thing for them to do. And I really like how that improves the quality of the analysis. So that's an example of we're making other changes here besides just going to single step. And so, if you're gonna do it now, because people won't want you to do changes every year. Let's go back to this topic of weighted analysis or marker selection and really describe what it is. So, the geneticists in the audience will know what we mean when we say a Bayes C-pi evaluation, and that's where you set a prior in the analysis that says, what is the probability of the marker having zero effect, the prior probability of each marker having zero effect. And so you take, we impute up to 50K genotypes to start this whole process. So it's basically 54,000 markers. And we get rid of the sex chromosomes and the unassigned markers. And then we start sampling in a Gibbs sampler which markers actually enter the model and which ones don't at each sample. And you do this over and over, tens of thousands of times. And this plot shows you then a plot of about 2,000 markers that on the bottom axis is standardized birth weight marker posterior values, and the vertical axis is standardized post-weaning gain marker posterior values. This is for 5% of the markers. So this analysis started with a prior of 95% probability markers don't enter the model. Which ones actually entered the model at 5%? And there's about 2,000 that entered the model in either birth weight or post-weaning gain at 95% of, or at 95% of the time. They actually were selected by the analysis at a 95%, what's called a posterior probability of inclusion. And I really like this plot. It illustrates a couple of things. First of all, it illustrates the pleiotropy among the markers, where obviously lower birth weight is, these markers are also causing lower post-weaning gains, or associated with lower post-weaning gains in the lower left quadrant and the upper right quadrant, higher birth weights but higher post-weaning gains. The thing I really like about this plot is the proportion of markers along the zero axes that have an effect on only one of the two traits. If you get more rigorous with your selection of markers here, so these are markers that entered the analysis 30,000 times in 40,000 samples, and some of these markers enter 100% of the time, and a lot of them enter at higher levels, and I'll show you some Manhattan plots of other traits to help you kind of understand that. But there's still all these pleiotropic markers in here, and those are really the genes that you probably can't have a whole lot of impact in changing their frequency through selection, because they're antagonistic in this case. The ones that are going to change birth weight are these, and the ones that are going to change post-weaning gain are in here. And that's a real neat illustration of what happens when you do these marker selection models. You can really get a picture for what is impacting these traits and how. The other thing that marker selection does do is it squeezes a little more accuracy out of the same information. And what you're looking at here is a graph from just one of our studies where we looked at this. The vertical axis is the prediction error variance, so that's the inverse corollary to accuracy. Prediction error variance is part of the accuracy computation. And along the horizontal axis here is the prediction error variance from BLUP, from just a pedigree BLUP, sorted by low prediction error variance, so high accuracy, to high prediction error variance, is chopped up in 10 categories. So the animals just chopped into 10 equal size categories, low to high accuracy. And you can see the top line here is the prediction error variance from pedigree BLUP, and you would expect then that's the lowest accuracy. The next line down is a Bayes C pi of 0, and that's the equivalent model to an SSG BLUP. And you can see the accuracy improvement that we got in this. I think this was a birth weight trait or something. Yeah, it was a birth weight trait. The accuracy did get an improvement in this data set when we set a pi of 0.95 in this super hybrid model. This was the accuracies that we got, and this is just among the genotyped animals, only among the genotyped animals. So you can see a pretty substantial improvement, especially on this end where this is the lower accuracy animals. These are the younger animals, and those are the ones where you really want to make the improvements. And so we think that it's an important feature to be able to implement marker selection models to squeeze that additional bit of accuracy out. The other thing that we've done here too, the other change, is that we now calculate our accuracy using a Gibbs sampler. And this is a subtle but important feature of the analysis. In fact, if we didn't do this, we could actually solve this problem in just a few hours for the largest evaluation, for the IGS evaluation, which is a huge evaluation. We could solve this problem in just a few hours, but we chose to do Gibbs sampling, which turns it from a turn time for the entire analysis from just a few hours into a few days. We'll still be able to turn this weekly in that evaluation, but it takes a long time to sample these models to get the prediction error variance out. That's actually a much harder thing to solve for than it is to solve for the EPDs. But there's a very important reason why we do this, and it only really became apparent once we started seeing the results of solving for prediction error variances by sampling versus what the current methods all use. The current methods implemented in IGS and in Hereford and others all use an approximation method, and there are several approximations out there. And we've always known that the current accuracy methods that use these approximations aren't too bad, particularly on high accuracy animals. It turns out they're not very good in situations for middle level accuracy, medium accuracy, think dams or young sires just coming in getting their first progeny, or low accuracy animals. They're especially horrible for. These approximations are especially bad at resolving good estimates of prediction error variance for those situations. And then they're particularly poor approximations when you're relying on lots of correlated trait information to make the predictions and the prediction error variance estimates. So for example, think when you have ultrasound scan data you're trying to use to predict carcass traits. Those approximation methods horribly overestimate the accuracy, underestimate the prediction error variance for medium and low accuracy animals in those situations. And you couldn't really see it until we started actually getting sampling based methods, because they're a direct method for assessing prediction error variance. The sampling does not suffer from the kind of bias that you get in estimating prediction error variance when using approximation methods. And we've tested that. You can actually obtain from these linear systems the exact inverse elements, the exact prediction error variances from the linear systems, but you kind of have to do it one at a time, and there's an algebraic trick to do it, and you could never actually implement this in these evaluations in any tractable way, any feasible way to do it. But implementing it through sampling, we've shown that when we go and grab the exact prediction error variances that we can solve for and compare them to the sample-based methods, that we get the same number. We get virtually the same number. And so we've proven to ourselves and our customers that these sampling methods do give us the true prediction error, or a high-quality estimate of the true prediction error variance. Unfortunately, because the approximation methods bias accuracy up and can bias it up substantially, now that we have these direct methods for assessing prediction error variances, the accuracy values drop. And not for the high accuracy animals, not really very much for high accuracy animals, but for middle and low accuracy animals, we get substantial drops in accuracy. And that's especially for young animals. And you can see why if you look at the BIF accuracy equation. If this prediction error variance is going to be higher for the sampling-based method than it is for the approximation method, then the accuracy is going to be lower. We've worked through with our smell committees and our advisory committees. We're working through the process with IGS. We've worked through it with Hereford, and they tend to take it very well. They're surprised, obviously. That's probably where a lot of the phone calls are going to come from. They're surprised that the approximation methods were not as good as they were, but then they start to. It's a funny process. They start to really feel like, oh yeah, okay, this explains a lot why our possible changes, we get many more animals changing larger than the possible change. And they're starting to wrap their head around it. On top of it, since the data cutoff was performed too, they're getting some accuracy drops just from using only newer data, and so all of that kind of blends together in the AHA situation. Here's my last slide. I'll wrap up here in a second. I just wanted to show you this. The other thing we've changed in both these analyses is in AHA, we've added or replaced their existing sustained cow fertility with a random regression model of Gem-Rozic, and we've converted the IGS stability to this same model. And basically, the reason is first of all, Gem-Rozic showed it's a really good model. It's at least as good as the threshold models. It uses more data. It can use data from contemporary groups with no variation. It handles missing values and observations at younger ages very well, very elegant kind of solution for it. So the accuracies go up on these predictions because of the way the model handles data better. It also is easy to implement in these marker effects models. It's very easy to implement. We get great marker effects solutions, and what you're looking at is for the Herefords, it's the proportion of marker variance described by marker windows, 1 megabase windows of markers combined together. And you can see there's some substantial amount of variation described by some of these marker windows. And we're seeing this in a number of traits, and it's really exciting to see that sustained cow fertility or sustained cow production does have significant major gene effects here. We've been able to repeat this same sort of thing in other data sets to see this in here. But you can see what happens here in these marker effects models. Where we do the Bayes C-Pi, the variable selection models, you can really see how it really resolves out these marker differences and really cleans up that kind of signal that you get from markers in these models. And so we're really excited about this trait and this implementation too, and we continue to study it fairly closely. With that, I'll turn it back over to Bob. And is there a Q&A now, Bob?
Yeah, thank you, Bruce. Appreciate that presentation very much. Very interesting results there. And I agree the last bit on the stability, sustained fertility has been a pretty substantial development and improvement in that analysis that I think obviously stability, sustained fertility, really important trait economically for beef producers, and adding a lot more data to it's helpful. So there's opportunity here for a few minutes for questions. If we've got some of those from the audience or fellow panelists, feel free to chime in as well. If you are just a regular attendee, you'll need to click on the little chat button at the bottom of your Zoom screen, and that'll extend your display a bit to include a chat window, and you can post up questions to our group. So. Anybody's out there got one? I'll throw one at Dr. Miller. You know, one of the I think real challenges of the single step, or one of the benefits rather of single step is computational time. As we think about you know, the rapidly expanding inventory of genotypes at American Angus, how might that sort of influence processing times, and you know, what do you anticipate moving forward to sort of mitigate some of those challenges?
Yeah, I didn't highlight this, I guess, Bob, it's important to point out. Up until 7/7, you know, the data cutoff every week was actually, geez, what was it, Tuesday afternoon or something. So we called it a weekly evaluation, but it really only took a couple days. between when we cut the data off. It was Monday afternoon. It doesn't seem that long ago, but I have a bad memory. So, it was sometime between the early in the week and then new results rolled out Friday morning. So we called it weekly, but there was less than a week there where we actually used to run it.
Right.
And we actually had a window there where we could actually run it twice. If you ran it and there was some issue or something, you had a chance to run it again. Single step, our analysis does take longer than what we previously were running. So we've backed the data cutoff to Friday. So really it is a week now. Breeders got to get their data in for Friday for new results the following Friday. At the moment, that's our plan is to stick with that. But as we get down the road, we'll probably reevaluate it. But at the moment, we're kind of sticking with the weekly evaluation.
Gotcha. Excellent. Let me pull up the chats here if I can figure out my modified screen here. Question posted from Ignacio. Thank you. It says, what can we I'm just trying to read this here. Sorry, my glasses aren't working well. Getting old and progressive lenses. So it says we can weight the accuracy for the traits in Angus breed and other breeds in the future. Is it possible that the technology can increase the accuracy of the genomic traits? So I think a little bit of prognostication maybe about how some of maybe new marker panels or other developments on the genomics front increase the utility of the genomic data. I throw that to either Bruce or Steve or both. So,
yeah, Bob, I can take a first kick at it, and then Steve follow up. I think our best bets for improved accuracy, getting more genotypes in at some point, the marginal value for improving accuracy goes down. But that we aren't at that point, and we have special problems with maternally influenced traits like milk and even stability. We need a lot more genomic information on females. But I think our best bet, at least in the intermediate term, for improving the accuracy of the genomic portion of the predictions is the work that all the good scientists are doing in looking for functional loci, and as that evolves, we anticipate that having better markers that are more closely associated with gene function will benefit from improved accuracy.
Yeah, one of the other developments we've put together recently is developing a chip for Angus cattle, which we call Angus GS, which we'll officially launch at our convention here in November. But that's an example, I guess, of new genomic technology, which actually allows us to reduce the price. So, the price of genotyping is dropping from $45 to $37, but the actual density is going up. So we're going to have 50,000 SNP markers now coming in on all animals. Before, with low density testing, we had an imputation step, which was highly accurate, but still it's better to get the targeted genotypes in all the animals. But part of that chip development is we actually could design, what are the SNPs that are most informative in Angus, and we have some regions that we're particularly interested in, so we actually put more SNPs in those regions. And all those SNPs based on other genotypes we know are polymorphic in Angus. As Bruce mentioned, the 50K has 54,000 SNPs, but in Angus, when we start to throw out the SNPs that don't work, we're down close to 40,000. So we can actually, so that's, I think, one thing is basically a better tool, a better chip. And the other thing is just more data. We can do increase accuracy and increase accuracy for more traits, but it's a matter of getting more phenotypes in. Carcass, we have 2 million ultrasound records, but only 100,000 actual carcass records. And so we actually have a program underway at the moment we call structured sire, which are, what are some high-use bulls that have got a lot of ultrasound projects but don't have carcass records. So we're actually getting cows mated to those bulls and going to get the carcass data in. So it always comes back to, genomics is great and it's increasing accuracy, and but we can't do it without the raw data. So basically programs to try and get accurate raw data in animals that are genotyped. That's going to be pushing accuracy in the future.
Great, thanks, gentlemen. One more question here, and we'll use this one to kind of dally off. We're at 1:15 here Central Time, but Kim Davenport posts up, says that presumably the Mendelian effect is a combination of both independent assortment and recombination. Are there any efforts to address these factors independently? So an insightful question on the Mendelian sampling bits.
Yeah, I don't really have an answer for that one.
Yeah, that's an interesting question. I was thinking just in my head how one might even go about that. So, Bruce, any thoughts there?
No, but it sounds like you need to put a grad student on that one.
I think so. Maybe we'll recruit Kim, right?
Yeah, there you go.
Yeah, that'd be great. Kim, thank you very much. That's a great question. Maybe that was an easy one to handle. We've got one more quick one. Kim says she is a graduate student. Well, Kim, get to work. That'd be great. Will it be possible to use the 10K bead chip in beef cattle in the future with less price to customers, similar to what other breeds, Jersey and Swedish Red and Denmark, are using on the dairy side? I know a number of breeds have gone to super or ultra LD panels. Maybe both of you speak real quickly about how we use imputation to sort of address on it. Carlos is based in Mexico and maybe not quite familiar with our sort of plans to make that implementation stateside. So
maybe just quickly for me, I mentioned the Angus GS chip. We put 50,000 markers on there. I think just with the volumes that we're doing, we can deliver 50,000 markers. A 10K wouldn't drop the price for us enough to justify it.
Yeah, in the IGS data set, of course, what do we have? It's more than half a dozen different chip versions and densities, and they're all being used to impute to that 50K density. It is a real moving target. But having done it, the quality of the imputation is very high. We've done quite a bit of testing, and others have too. The imputation up, as long as you've got sufficient background to do it against, imputes at typically 98% of the original density of the 50K density. So I'm not too worried about it right now. But I think having markers that are much more closely associated, being able to do variable selection to identify markers that are better for future generations of chips, especially functional chips, is going to be the key. I think we can get down to lower density chips with functional genomics and still achieve the same levels or better levels of accuracy.
Great, good thoughts. Well, gentlemen, Steve and Bruce, thank you both for both your detailed talks today and your presentations to our brown bagger group, and certainly the homework you did to get those presentations put together. I think a really exciting time here in beef genetic evaluation and technology advancement to help producers breed better cattle. And so again, thank you both for your work and contributions today. As we kind of wrap up, we'll look forward to joining or having you join us next week as attendees for session 2 on October 11th. That's next Wednesday at noon Central Time. And the title for that session is Implications of Beef Cattle Adaptability. Dr. Spangler at UNL will be hosting that day. And our two speakers will be Dr. Jared Decker from the University of Missouri. Will provide an update on USDA adaptability project he's leading. And Dr. Mike McNeil from Delta G will provide a discussion on how we can utilize genetic by environmental interactions. So look forward to that. In the meantime, if you've got questions or ideas and suggestions for future topics, don't hesitate to drop us an email. We look forward to having you join us next week. Thank you all.
Thanks, Bob.
Thanks a lot, Bob.
All right. Thanks, Steve. Bruce, you guys take care. Thanks.